The Physics of Interstellar Travel, Chapter 15, Communication. In this chapter, we look at the issue of sending electromagnetic signals over very large distances. An interstellar spacecraft is likely to have a small, low-power transmitter, and diffraction will spread its transmission over an enormous area. Remarkably, it nonetheless appears possible to receive reasonable amounts of data at the Earth from a very distant spacecraft. Interplanetary spacecraft already have to send data over large distances. The New Horizons spacecraft, pictured here, encountered Pluto in 2015 at a distance of 32 astronomical units from the Sun. The spacecraft sent back its data with X-band radio waves, a wavelength of 3.6 centimeters, using a 2.1 meter diameter antenna powered by two 12-watt transmitters. These signals took 4.5 hours to get back to the Earth, where they were received by a 70-meter diameter antenna, part of the Deep Space Network. This link could achieve a data rate of 1 to 2 kilobits per second. As New Horizons had 6 gigabytes of data to send, it spent the next 15 months transmitting the data. Now, Proxima Centauri is about 8,000 times further away than Pluto, so all other things being equal, the signal beam from Proxima Cen will diverge 8,000 times more by the time it gets to the Earth. We looked at the problem of diffraction in Chapter 11 in the context of laser sails. We now consider the laser as the transmitter and the sail as the receiver. The angle alpha is the diffraction angle, which depends on the diameter of the transmitter and the wavelength of the signal. It's then straightforward to derive a relation for the received power in terms of the transmitted power, the areas of the transmitter and receiver, the wavelength, and the distance. This is known as the Friis transmission equation. From this, we can also compute the rate of arrival of photons at the receiver. Note the dependence of the received power on the square of both the wavelength and the distance. Now, we can't do anything about the distance, but this relation favours using the shortest wavelengths possible. Note also that any decrease in the area of the transmitter can be compensated for by a corresponding increase in the area of the receiver. This is good because mass, and therefore transmitter area, will be very limited on an interstellar spacecraft. This table from the book shows the received power and photon rates for various configurations. The second row corresponds to New Horizons, assuming it used both transmitters. If we move New Horizons to the distance of Proxima Centauri and use slightly smaller and rounder values for the power and transmitter diameter, the power drops by 9 orders of magnitude. Using instead a near-infrared wavelength reduces the diffraction losses, increases the power, even if we use just a 10-meter receiving telescope. Although, given the much higher energy of the photons now in the near-infrared compared to the radio, we are now receiving just a couple of photons per second. This could be increased by using an incoherent array of, say, 100 receiving telescopes. The main takeaway messages from this are that we want to use visual or near-infrared wavelengths to communicate, but that we still need large telescopes to receive the signals. Now, optical communication is common over fiber optic cables, but it's less common in free space. However, in 2023, NASA tested optical communication from the DSOC experiment on the Suka satellite. This sent signals a distance of 3 astronomical units to the Earth, where they were picked up by a 5-meter telescope. So far, we have only considered received power and photon rates, but what we are actually interested in is the received data rate. How much data we can send with a given amount of power depends, in particular, on how much noise there is. When sending and receiving electromagnetic signals, there are many sources of noise that can corrupt the signal. Some of the photons may be lost by absorption in media. There may also be an interfering source that adds photons to the signal. A particular case here is the very bright target star, which, as seen from the Earth, has a very small angular resolution, very small angular separation from the spacecraft's transmitter. Communication can be seen as sending a message over a so-called noisy channel, which is shown schematically here. I talk about modulation in the book, but I'll skip it in this video. Noise means that the signal sent is not the same as the signal received. Because noise also affects terrestrial communication, such as sending data over the internet, there is a whole industry concerned with methods of so-called error correction to mitigate the effects of noise. I won't go into any details here, but what this boils down to is adding redundancy to the signal. In its simplest sense, this would involve sending the signal multiple times. The idea is that with sufficient redundancy, we can identify changes to the signal caused by noise and correct those errors to reconstruct the original message. Adding this redundancy is done by encoding the signal. This makes the signal longer, more bits, so there is a price to be paid. The art of error correction codes is to provide sufficient redundancy in the least possible space by adding the fewest extra bits. We might think that at any given noise level there will be some minimum rate of error in the received signal. Remarkably, this is not the case. It was theoretically proven in the 1940s that it is theoretically possible to communicate over a noisy channel up to some maximum data rate with an arbitrarily low probability of error. This maximum rate is called the channel capacity. What the stated theorem means is that for a given noise level, we can send data at a rate up to the channel capacity with essentially no errors. The actual error rate depends on the error correcting code used. A good error correcting code allows us to specify the acceptable error rate and will then tell us the actual data rate that can be achieved. Another remarkable thing is that since the 1940s, error correcting codes have been invented that can get quite close to the theoretical limit. An important aspect of interstellar communication is that signals take many years to get from transmitter to receiver, so it will be essentially impossible for the receiver to ask the transmitter to resend corrupted data. Because data will probably be received over timescales of years, and because we cannot guarantee that the receiver will never have any interruptions, the error correcting codes need to provide a redundancy over long time periods, longer than any expected interruptions. Interstellar communication will involve such low signal powers that with optical or infrared wavelengths, we get into the realm of having to count individual photons at the receiver. To maximize the channel capacity, we then have to consider how many bits of information individual photons can carry. Perhaps counterintuitively, the answer is quite a few. See the chapter for why. Experiments have been done demonstrating photons carrying 10 to 20 bits per photon. Several authors have performed theoretical case studies to see what photon and data rates could be achieved for interstellar spacecraft in the Alpha Centauri system. Let's see what they can do using the Friis transmission equation. This first study adopted a 1 kilowatt, 10 meter diameter transmitter operating at half a micron wavelength, received by a 200 meter diameter telescope on the Earth. This system is large enough that even taking into account a factor of 10 losses compared to the Friis transmission equation, 1 million photons per second are received. They don't discuss encoding, so they don't actually give a data rate. The next study uses a longer wavelength, a lower power, and smaller mirrors to give 288 photons per second. Adopting some encoding scheme, this corresponds to a data rate of 260 bits per second, although with a large error rate of 1 in 1,000. The biggest source of noise is assumed to be light from Alpha Centauri. This study is for a flyby mission, so it also takes into account the fact that the received signal is redshifted. This third study uses an enormous array of receivers with an area equivalent to a 10-kilometer diameter telescope. The transmitter is also large, although the power is modest, and with this system we can in principle receive 390 megabits per second, enough to stream video. The final case study assumes a high power, but more realistic optic sizes. It assumes the light from Alpha Centauri can be entirely blocked with wavelength and spatial filtering, so that the Earth's atmosphere is the dominant source of noise. I've omitted most of the mathematical details in this summary of this chapter. Communication is a big topic that quickly takes us into issues of engineering. In the book, I just look briefly at the concepts of modulation, encoding, noise, and bandwidth, and give expressions for the channel capacity for classical channels and for communication at low photon rates. There's a lot more to explore here, so check out the references in the further reading section at the back of the book.